Liam, Fedus, and Barret Zoph of Google Brain, welcome to the Data Exchange podcast.
Yeah, thanks so much for having us.
All right, so as I warned you folks right off the bat, since a lot of our listeners may not be aware of the nuances of Google, so what is the mission of Google Brain, or for that matter, what is Google Brain? So Liam, since you have more seniority, I will let you answer this question first.
Less seniority, but I'll still take a stab at it. Yeah, so Google AI is sort of like a broader encompassing of a lot of like Google's research missions, primarily in machine learning, but there's also machine like systems engineering and a lot of different types of research, including like math. Google Brain is perhaps sort of like a more of a legacy term of a smaller sub-team. This was created in 2012 by Jeff Dean, Kwok Lee, and a few others. So this is like sort of the team that Barret and I have joined a few years ago, and it's like a sub-team. And really the goal is just putting forth like, some of the best like machine learning research. And I think it's done like a really good job of sort of balancing research and engineering.
So Barret, as I pointed out in some papers, there's someone from Google Brain and there's another person from Google Research. So what's up with the difference between, is there a big difference between these two teams?
No, I think, there's the kind of the Google AI as a whole, and there's like, a lot of different cross collaboration, and, Google Brain is just kind of like a smaller team within Google AI research as a whole. But, I would say the org is very, collaborative and everyone works together.
So in your folks' day-to-day work, is the goal to publish papers or to build systems or to deploy to product or a mixture of all? So how would you apportion your time?
Really quite a mixture, honestly. So Barret and I, like by title, are research scientists. But there's also sort of like a research engineering ladder. The research engineers might be a bit more focused on sort of building the systems or the infrastructure. And then there's sort of like a subgroup of people who are then really focused on getting some of this like machine learning technology into products. But honestly, like the lines are very blurry. Researchers doing engineering, engineers are doing research. Just sort of the field has sort of evolved for some of these like larger scale efforts really require like a balance of both. Like this designation is not like a clear one. And so Google, or Google Brain at least, we have a huge amount of freedom. If you want to sort of try to productionize tools, you're welcome to do so. If you want to publish papers, that's great. You're sort of encouraged to do so. But it's really, we're given a lot of flexibility, and people choose what they want, how they want to use it.
So how did you folks end up settling on the problem of scaling language models? Because as far as deep learning, there's many directions you can go, right? So you can go into computer vision, you can go into speech technologies, which Google is also strong at. So why did you choose language?
Yeah, really great question. So actually, before I was working on language modeling and scaling language modeling, I was actually doing a lot of work in computer vision, especially related to, for computer vision, being able to make use of like unlabeled data and being able to do like, multimodality related things, just because in computer vision, a lot of the times labeling something with, very fine grained labels at each pixel can be very expensive. So it's a very important problem. One thing that made me very excited about working in the language space is that I think language is kind of this very like core fundamental way that like, people just communicate and store information. And it seems like a very like, core piece that needs to be, done very well to get at like really, intelligence. And it's just such a medium that's used through so much from either like communication, storing information. And I think that when I was looking at the space, like one thing that definitely really excited me was a lot of the really great works around scaling some of these models, including, some of the scaling law research from OpenAI and everything. And I think this is something that, really excited me and made me kind of move more into the space.
So Liam, the building blocks for how we got to where we are today are what? So one of them would be transformers, right? Because transformers allow you to work with largely unlabeled data, and you can parallelize them. So there's a lot of advantages. So what else have brought us to this moment in terms of language?
So I would actually caveat that. So transformers don't necessarily, they're not the only type of algorithm that sort of permits this sort of self-supervised algorithm. Like another really great aspect of text is you don't need to generate labels for it. So if you have a sentence and you're predicting the next word, or if you're sort of filling in the blank, these are really wonderful self-supervised algorithms that don't require an additional human to come in and kind of label like as like it is would have for an image, like, oh, this is a cat, this is a dog. So recurrent neural nets was sort of like the paradigm before 2017, and you could run the same sort of algorithms on that before. Transformers, though, are just insanely well adapted for the accelerators we have. They have sort of this like kind of reframing of treating a sequence sort of like over time to sort of let's try to operate on the sequence in parallel. And this has been like extremely hardware efficient. And what we've been able to do is through sort of specialized devices, scale up the models many orders of magnitude. So I think it's just language is sort of abundantly available. It's publicly available. It has a good self-supervised algorithm baked into it, which is predict the next word, fill in the blank, and then transformer plus a huge amount of compute has really sort of enabled this. And I think like organizationally, it sort of relied on teams, kind of like huge teams sort of taking part in this. I think early in machine learning, like really wonderful research could be done by like just a handful of people. But now for some of these like really large scale efforts, it's sometimes 10, sometimes over 100 people collaborating across like infrastructure, research, engineering, all to bring together like one of these things. So there's like really like significant organizational challenges too.
Speaking of Google Brain, actually transformers came from Google Brain, right?
Yes.
And
that's right.
So Barret, maybe make it more concrete for our listeners in terms of what class of language models were you folks, or are you folks attempting to scale? Are they the ones that people hear about, like the GP3 type model? So what exactly are you trying to scale?
Yeah, so this is a really great question. So yeah, all of the models we've been working on are definitely, transformer based. So basically during training, we're, able to operate on the whole sequence in parallel. So it doesn't kind of have this like, where in RNNs, like you kind of have to wait for the computation from the previous token to be done to move on to the next token. In terms of model class, I would say right now in the NLP space, there's like 3 different types of models. One is like encoder only, which is BERT. So you have a sentence and the goal is to just create like a really good representation that you can then do stuff with it, like sentiment analysis, all of these different types of things. Then there's another type of language models called decoder only models, which is just like the GPT-3 and a lot of these other language models where you're just focused on, predicting token after token. Then there's a third class where these like encoder decoder models, I think like the T5 work from Google really helped popularize these, but there's been a lot of work on them. And these, you have an encoder part where you have some like, sentence or some kind of amount of text and you kind of like encode it. And then based on that encoding, you start predicting text. So we've actually, I think there's been a lot of work studying these, and Liam and I's work has focused on transformer models that are encoder decoder type models. I think a lot of the reason times because they actually seem to do well for a lot of fine-tuning tasks, especially where like the amount of text you're being generated is typically shorter. So a lot of our work is studied on like, fine-tuning on like a lot of common benchmarks like superglue or even some summarization tasks, question answering, where the amount of text isn't as large that you're generating. And we find that these models are just like very, very effective. So we've studied a lot of our work on scaling these encoder decoder style transformer models.
So Liam, how much is enough for these language models? So, they keep getting bigger and bigger. And obviously that's why you folks have been trying to make it more efficient to scale them, right? So
right.
What's the sense in the community? So at what point is there really diminishing returns?
Well, I mean, like right now, there's been some like recent work from DeepMind. The paper is called Chinchilla. And in it, they're sort of suggesting that maybe we're starting to see some sort of like diminishing returns in these sort of like power law scalings scaling dynamics. So there's a really famous paper from 2020, Kaplan et al., which sort of put forth these like neural scaling laws. And they're like, well, if you just simply increase the amount of parameters to compute the data, you get these power law relations in the loss. And so it just sort of gave this like extremely reliable thing to produce like very good models. It's just, oh, okay, follow this paradigm, follow this recipe, and you're going to have a great model. But now it seems like, okay, maybe we've sort of been over-indexing on the size of the models and we need more data. And at some point, you're going to sort of like reach like the entropy of the language, like for some sequence length. So at that point, you can't do better than that. Like there's like some underlying uncertainty in our language and you can't model past that. And maybe we're starting to see some slight curvature as we would expect. I still think we have a long ways to go. And then you could continue to push like the sequence length. So it's like one thing to sort of model down to the entropy of language for like, n-grams, where that's pretty simple. But like if you can do like the entropy of language at like 1,000 characters or something, or like 1,000 words, that's getting really significant. So right now it seems like we need more data, and we're looking for all sources of that. And then at some point, like let's try to incorporate like other modalities, but that's a little further on.
So Barret, give us a sense of what kinds of how efficiency metrics did you guys come up with? Like, I assume that you went from a smaller model to a larger model, but then decreased training size. But give us a sense of magnitudes of improvement.
Yeah, so one of the techniques that Liam and I spend a lot of time thinking about is sparsity. And this, so in a standard, transformer model, let's say, but most deep learning models, all inputs to the model will use the same parameters. And sparse models are a way such that, depending on what the input is, they can each use a different subset of the model parameters. And so this allows you to have, roughly the same amount of compute per input, but have many more parameters in the model. So we were looking at this as an efficient way to improve the scalability of models. And, I think one of the key metrics we look at is just, for a given amount of TPU, GPU hours, what model gives you the best performance? So this is kind of like a very simple and clean setup where it's like, okay, I give you 100 GPUs for 10 days, what's the best model you can produce? And I think this kind of drives a lot at what improvements are good versus what improvements are bad. And in terms of our sparsity work, we were finding in some of the best setups in terms of making our method, in terms of our method, showing good progress, we were getting around like 4 to 7x compute savings. So you could, basically in 1/4 or 1/7 the time get to the same model quality as you would before using sparsity.
So what are are these language models multilingual?
Some are, some are not.
Okay.
We've trained a mix of them. I think like people have gravitated towards multilingual training. It seems like the models just sort of readily handle all the languages we pass in, and it's just really great to be able to communicate with like a larger group of people. So I think the trend is absolutely towards multilingual.
And so in terms of, so you alluded to this earlier, Liam, that in this area, it's actually quite hard for, honestly, academics to compete, right? Because not only do they not have much compute and maybe not much data, but at the end of the day, I think the biggest bottleneck is maybe not enough systems engineers to actually pull it off. So how many groups are involved at the bleeding edge of Barret? What the types of things that you folks are doing? Is it really a handful of groups in the world?
Well, I actually think that, so for one, like a lot of the times when people are trying improvements, it's actually on much smaller setups and scales. And, I think we've actually found a lot of improvements and just from like a lot of good research papers, even from, academic labs that, when these ideas scaled up actually work really well. So I would say the base of people really meaningfully contributing and collaborating on this types of stuff is like really high. And even people with lower amounts of compute can still be running like really important experiments and contributing like really important ideas to the field as well. By
the way, so the one thing that I think that is worth emphasizing is that there's not going to be a singular language model, right? So in the sense that, depending on your situation, you may have a language model that's massive that's in the cloud, but you may have a language model that's much smaller in the edge. So there's actually a lot of opportunities for people to build many sorts of language models. Am I wrong in this, or?
No, I would say you're absolutely right. Like typically you want models of all different types of scales for different applications. Some need to run faster than others. Real-time machine learning is very big too. So yeah, you really want like fast and small models. So yeah, I mean, I think that, almost everyone can be, meaningfully contributing towards like pushing the progress forward of these types of models and algorithms.
So at
I
this
think it's also possible in the future. Oh, sorry.
No. So I was going to say, so at this point, training is really, do you have to have a very specialized setup for training at this point, like a GPU cluster or TPU cluster with fast interconnects and so on and so forth?
To do models at like, a sufficiently large scale, then yes, you definitely need to have like specialized hardware, because the model is just too large to fit on a single accelerator. So now you have to sort of split the matrices, split the tensors across a bunch of different accelerators, but now you still need to sort of pass forward activations or pass around gradients. So that requires communication between the accelerators. If the communication is too slow because they're not interconnected, then it just like will really encumber your training. So these largest models are all sort of built on like very like, fine-tuned kind of like hardware and like, data centers. But again, like Barret was saying, it's like if you're an academic, you can still run, small things like within like a single node, where it's just a few internetwork devices.
So Barret, are there any innovations on the modeling side so that you can do everything in CPUs?
This is a really interesting question. And, I'm actually not even the most up to date with that, but I would say I haven't heard of too many things of, these models being run on CPUs. But, for example, in vision, all of the models used to be for phones, especially were like, designed for CPUs, but it's kind of interesting also now switch of where now even phones are starting to have, more GPUs and stuff on them as well. But yeah, for like a lot of applications, you really want CPUs, but I'm actually not super up to date with the literature on that, but I would be very optimistic about, there's a lot of smart people out there trying to figure out how to do this in a good way.
So the efficient scaling stuff that you folks work on, what's the path from what you do to getting it into the hands of practitioners? So does it end up on Hugging Face, or so how do people get a hold of the latest and greatest in language models?
Yeah, well, so certain organizations will sort of like put forth their models through APIs.
Yeah.
I think including Google. So OpenAI will sort of have APIs, and a bunch of like startups and Google will sort of surface models that people can use. That's one way. And then there's sort of been some like open efforts to sort of train the model. Like I think the big science effort is training a GPT-3 scale
or just even the embeddings,
Oh yeah, well, I mean, some models are sort of open sourced. Like BERT is open source. The T5 models were open source. So there you could do generation as well as like retrieve embeddings. Some of the very largest models that Barret and I have served or have trained have not yet been served. But one way would be like through an API.
I see. And at this point, so what is the connection between? So do you folks work on other things like? One of the things I came across with recently is super interesting in language models. I don't know if you folks work on this, but responsible AI meets language models. So the detoxification of language models. Have you guys heard of this? So it's basically the idea here is that if you take something like GPT-3, you can't release it in the wild necessarily. You have to put guardrails around it. But then it turns out that if you put guardrails around it, the performance kind of diminishes. So it's like an interesting research area for people.
Well, GPT-3 is sort of getting released through some of these like APIs. And I think there's been sort of a lot of work on sort of like aligning the models towards like the things we care about. So for instance, like we pass in some instructions to the model as like part of a few shot prompt. We sort of hope that the model sort of like understands what we're trying to do and sort of executes faithfully on that. So a lot of teams have been sort of working on this sort of like alignment perspective to make sure that we can do this. And also, like you're alluding to, there's also sort of like multi-stage pipelines where the model might produce many different options, and then the same model or a different model might look through them and say, like, determine, is this sort of a safe response? Is this sensible? Is this like specific to what the user was asking? And with these like kind of multi-stage pipelines, then you can produce like, you know, even better results to the user.
So Barret, you worked a lot in computer vision. So what's happening in computer vision in terms of the type of work you're interested in, efficient scaling? Do they have similar problems in computer vision around video and things like this?
Yeah, definitely. I mean, actually, some of the techniques Liam and I have been working on, like, you know, model sparsity, where each input can get a different subset of the model weights. Like, there's been a lot of really interesting research on like applying these techniques and innovating the techniques as well in computer vision. So I think one thing that's actually really cool is that there's starting to be a bit more of unification across the different spaces. You know, we have transformers in language, we have, you know, VIT for vision. And now a lot of the times the modeling decisions and algorithms can be very easily, you know, translated from one domain to another, which allows really good cross collaboration and yeah, more easily flow of ideas. But yeah, definitely in these spaces, you know, for images and video, there's just so much of it. A lot of it's high dimensionality. There's a lot of really interesting problems on like, you know, how do we only look at subsets of the information we really want, make the models large to be able to, you know, absorb a lot of the information in these really large data sets. Yeah, so I would say there's like a lot of really exciting space there as well.
So what is doable or practical in the multimodal world in terms of, because, you know, if you take each of these areas, they're already challenging on their own, right? So like we've been talking about large language models. Now you're going to combine images, right? Or sound. So yeah. What is actually doable and practical as far as multimodal models?
Yeah, so this is a great question. There's been like a lot of really great work from a lot of different places, like Google, OpenAI, you know, to name a few is like DALL-E, where you're going from, you know, text to generating images to, you know, things like Clip and Align, where you're embedding images and text in the same space. So yeah, it seems like right now there's been like a lot of really good work on, you know, trying to at the very least get images and text embeddings into the same space. And that seems to be working really well. And I've also been seeing, you know, works here and there of actually now starting to do this with video and audio as well. So I think one really good thing is, like I was mentioning before, that now there's really starting to become like, you know, big unification of what the model is across many of these different domains, which makes it very easy to have, you know, when you have the same model, then all that you need to change is like kind of like the input tokens almost, which makes doing like multimodal stuff very easy. Whereas I think before, when people were using like convolutional neural networks in computer vision and then, you know, transformers in language, it makes it kind of harder to blend the models together. Not impossible, people were still doing it, but I think with the unification of the architectures we're seeing, it makes the research a lot easier now today.
Okay, so let's close with, so what are one or two things you folks are most excited about right now in terms of, it doesn't have to be modeling, it could also be tools.
Yeah, let's see. I mean, I think right now I'm very excited about more adaptive style models. So Barret and I have been sort of exploring adaptivity in like one sense, where we're adapting to like which parameters are we selecting for a given input. But a flip side of that is you could sort of adapt how much compute are you applying for each sort of specific example. And I think this is going to be really important. Like, as Barret was sort of alluding to before, there's some different kind of like latency constraints, and sometimes you want to be fast, sometimes you have more time to sort of process to get to like a better answer. And if the model could just sort of dynamically determine, oh, I'm sufficiently certain, like I've done enough processing, I'm gonna spit out the answer to you. Or, oh, this is a hard example, let me like use extra space. Let me use more time. Let me do additional compute. Let me like sort of rally more resources to give like a good answer. I think this is like really promising. So I think this like adaptation is an area that I'm particularly excited about.
Barret.
Yeah, so I mean, one thing I'm definitely very excited about that I mentioned before is multimodality. I think getting all of these different modalities into like a single space is going to allow for like really cool applications. But the second thing that I was going to say is like I'm actually just really excited about a lot of the really good data set research that's been going on. Like I think that a lot of time has gone into like modeling improvements, and I think there's been some but less time spent on like how do you figure out what's like a really good data set, curate larger data sets. I think especially in line with some of these recent papers that are like, hey, our model sizes are too big, we want to be training longer. This is going to really necessitate a lot of like getting more data, studying the data more. So I think this is like a really important direction in general. So I'm really excited to see more works in the space about this topic.
Data-centric AI, right? So speaking of which, actually one area in terms of data sets that I've never quite understood is summarization. Because summarization is subjective, right? So how do they create good benchmarks for summarization? And what? Yeah. So what is the gold standard benchmark for summarization? Oops.
Not like a singular correct example.
Yeah. Exactly. It seems like it'll come down to you have to have like a bunch of humans who will score the summaries, right?
Yeah, I mean, like in an ideal world, you have human evaluation.
Yeah.
Short of that, you have like simple like n-gram overlap metrics like Rouge or something. But it's really an impoverished metric, and I think a lot of papers have sort of shown that this only correlates very loosely with a human or subjective judgment of how good that summary is.
So while I have you folks here, I'm going to spend the last few minutes asking you about Google tools. So obviously there was TensorFlow back in the day, and then JAX. So are there any things that I guess you're not allowed to talk about it if it's not open source? But one thing that I saw recently that seems interesting is this thing called Pathways. I don't know if you guys are.
That's right.
Yeah. So is that something that's already being used internally inside Google?
Yeah, absolutely. Barret and I were actually just sort of collaborators on a recent paper called PaLM, Pathways a Language Model. So this is a 540 billion decoder-only dense model, and it used the Pathways infrastructure. Pathways was sort of very important for this because we were talking about like inter-network devices, and TPUs are sort of arranged in pods. And this was the first model that was actually trained across 2 different pods. And that was facilitated by this like more flexible framework, Pathways. And for the research that Barret and I do in terms of like sparsity, Pathways also sort of facilitates like more flexible type of models. So for instance, we do mixture of experts, and what that means is at a certain layer, you have a set of parameters or a set of experts. And usually when we're training these things, it's completely homogeneous. It's like a cookie cutter expert, they're going to have different parameters, but all the same like shape and size. Pathways is something where you can much more easily express something where it's like, oh, you have some small experts, some large experts. This expert does some recurrence, and just kind of like more flexible like computation. So this would be like very tedious or like impossible to express in other frameworks. Pathways sort of like opens up this kind of like possibility.
Yeah, I read the paper. It sounds very much like something I'm familiar with, Ray, the open source project Ray. I am full disclosure, I'm an advisor to the startup behind Ray.
Oh, great. Yeah, good work over there.
Yeah. So anyway, so thank you for taking the time to join me today. And thank you, Barret, for reaching out.
Yeah, no, thanks so much for having us. It's been a real pleasure.
Thanks, Ben.